Good morning, Ben Cohen. Time to talk about some transformers, motors, generators, DC-AC. Some of them. This is going to be a pretty broad overview. So, the reason I like to talk about these is because you already know all the information for how they work, but you really haven't been told how it gets put together. And so this is a chance for me to kind of wrap up the physics with like, hey, here's some engineering. Because physics by itself is pretty useless in life. My view of things is that everything in life is just tools to make food or electricity or something comfortable. And so math, for the most part, is just a tool for physics, and physics is just a tool for engineering. And engineering is where you get the transformers, the motors, the generators, and such. So we're going to start by talking about transformers. But I'm trying to think of how I want to draw it. So maybe if I do gray, and then I make this one white, and I kind of do one of these. Haha! So this is kind of like an iron core. And I'll group it together. Click, click, group. Nice. Excellent. You guys don't appreciate that as much as I do. So, So the idea with the transformer is it transforms high voltage to low voltage or low voltage to high voltage. Or one voltage to the exact same voltage. And the way it does that is it uses Lenz's law. Lenz's law, as you may remember, or should remember, is, let's do blue, an induced EMF is negative d flux dt, where this EMF is basically just voltage. So if we use this gold color for, let's say, copper, do some wire, we wrap this wire around one side, and then we wrap some wire around the other side. I'll do slightly less just to kind of show a difference. And we could call this one on the left the primary coil, the one on the right the secondary coil, meaning that current comes in this way and out this way. And it's one of those things where it's kind of disingenuous to say it that way because current goes in and out both sides. Well, let's say that this side over here is driven by some sort of AC electrical source. And there's no AC electrical source on this one. There's just, I don't know, a light bulb. I know you probably don't want to, you're probably better off than a light bulb if you're going to create this transformer. So the idea here is you have an electromagnet. Electromagnet is a coil, is a core. It's a coil of wire, and for practical purposes, they will almost always have an iron core inside them. Iron is pretty cheap, and it increases the effectiveness of the solenoid by a significant amount. You should look up how much that is. You could probably look that up. Okay. So the idea here then is draw some magnetic fields. So we have, let's say, the current going this way then through the wires, looking this as a solenoid, and using our right-hand rule, fingers go in the direction of the current, thumb points in the direction of the magnetic field. And so what happens, more or less, is the magnetic field is transferred along the iron core, like so. And with this AC current going through this wire, you have a changing magnetic field. So this is magnetic A over dt negative, which equals, do product rule, you get negative, and then see here, change of magnetic field with respect to time times area plus magnetic field times area with a change in area with respect to time. Well, the coils are pretty stationary. They're pretty much just on this iron core, and they're not going anywhere. So this part right here, bam, goes to 0, and you're left with change in magnetic field with respect to time. We have an AC current, so we have a changing current going through this coil, and that changing current will create a changing magnetic field. And so what happens then is you have voltage coming in this way and a voltage coming out that way. So the formula then that you'll have is you'll have your primary voltage, Vp over Np equals Vs over Ns, where P is primary, S is secondary, V is voltage, and N is the number of loops. So if you have a big number for your voltage and the same big number for your number of loops, then that would be the same as a small number for your voltage, small number for number of loops. So if you start with many loops on your primary, few loops on your secondary, then the voltage will go down. So you can have voltage high over here because many loops, and you'd have voltage low on this side. Now, you might think, wow, that's kind of magic. We just create a whole bunch of voltage. Kind of true, but it's also like a reduction gear or a transmission from a mechanical sense. So you can't create power. Power is energy. It's measured in watts, I think. And it's joules per second. So the idea is energy per second. Well, the energy on the left side will be, so I'll do power primary, power secondary. These will be the same. So even if your voltage goes up or down, I'll say power equals IV, power equals IV, which is one of the formulas we knew. No. Current tense. Then your current primary times voltage primary will equal current secondary, voltage secondary. So you could have high voltage, low current go over to low voltage, high current. And your thought process might be like, well, why does this matter? This is one of the biggest uses for this is power transmission. This is why AC, in many respects, is superior to DC, because it is relatively easy to make an alternating current transformer. It is relatively difficult to do a similar process with direct current. So by having this changing current, you can then create this changing magnetic field, which then can be converted using Lenz's law up here, E equals negative d flux dt, into a higher current. So the idea is a power plant will create a reasonable voltage. It will then go through a transformer. In power plants, they almost always create alternating current. And the reason power plants create alternating current is because they use rotating machines to generate this, generators. And rotating machines lend themselves easily to creating alternating current, the whole sine curve thing. And so then they transform this voltage to really high. It transports well across power lines, and then once it gets to wherever the end user is, it can then transform it down to something that's more usable. You really don't want to be using like 10,000 volt electricity in your house. And the reason for that is dielectric breakdown? I assume that's the reason. So the reason you can transport power, you want to transport power at high voltages. So if you remember your equation for power, we have power equals IV. But we also have Ohm's law, I equals V over R. So then this would also be V squared over R. Let's see, what else can we do? We could also say that V equals IR, just a rearranging of Ohm's law here. And so therefore we'd have I squared R squared over R, which equals I squared R. And you're kind of, when you're taught this the first time, you're kind of basically said that, all right, you have this power equation, you have Ohm's law, and you can convert between everything. Well, that's not actually entirely true. So these are three different power equations where this is power for generators and transformers for the most part. And this is, I guess, heat losses or I squared R losses. This is due to basically electrical friction within the power lines. When you have a current flowing through a resistor, this is the kind of loss you're going to have. So when a power plant will convert electricity for transport to send out to all the places, they want to minimize this loss right here. And the way that's done is by having a very high voltage. Because if you have a high voltage, you'll have a low current, but be able to transfer the same amount of power. So this is the power you are transporting. And so if you have the same amount of power and you have a very high voltage, that means your current will go down. And so when they transport to your house, that's why they want a very high voltage to minimize the I squared R losses. And that's the value, that's the biggest value you have from transformers. Allow high voltage for transport. Or you could say alternatively, low current for transport. One of the other, I guess, ancillary benefits of transformers is it isolates two circuits. So you have this circuit over here on the left, you have this circuit over here at the right, and electrically they are isolated, though magnetically they're not. And the idea here is if you have a voltage over here on the left that looks something like this, where right here in the middle, it's like, I don't know, 10,000 volts, and it goes up to 10,001 and down to 9,999. You have this massive DC current going through here. Well, when it goes to the transformer, that DC is filtered out. And so the idea is if you want to isolate it over to this side then this would just be from 1 to -1. Because this extra 10,000 volts DC over here would be filtered out, more or less. And the idea here is you can isolate your circuit from DC current, DC voltage or DC current, and I'll say DC voltage, because it doesn't alternate, it doesn't fluctuate. So your negative d flux dt, your change in flux or magnetic field with respect to time, will only be from the alternating current, not from the direct current. And one of the other benefits of a transformer is it can isolate from your DC current. So that's the idea behind transformers. So moving on to DC motors, I'm going to draw up a DC motor. This is going to probably test the limits of my artistic skills. Let's do this. I wonder if there's an easy way I can do it. Yep, I will try. Alright, so I'm going to draw a square like this. Whoop. Make it gray. There we go. And make the outside also gray. Perfect. Then I'll make a circle, like so. But it'll be white. Move it over here, make it slightly bigger, move it over. I'm surprisingly okay with that. Copy, paste, rotate about, less rotate, over here. Group everything together. Yes. Okay. So this is going to be my DC generator. So now we'll draw in some wires. So the idea here is we want a magnetic field between the two. So I'll do something along the lines of this. These are wires. I know it's a gold color, but I guarantee you when I make electromagnets, I do not use gold wire. Even though gold would be more effective than copper, it would not be more cost efficient. I'll go the other way with these. There we go. So this is the current. And so using, no, maybe I want to do the other direction. Can I just maybe? Nah, it's too cheesy. Goes down this way, down this way, down that way, down that. Now if I've already drawn half of them, I should probably finish it up. There we go. And then B for magnetic field. Red for magnetic field. So the idea here is fingers in the direction of the current, wrap around, and you get magnetic field. So we'll get a magnetic field going this way. And then I will draw a... There's probably a way I can do it with a square, but I'm not that talented. So I'm going to try and draw it like this. You have to forgive my artistic talents here, which are missing and lacking. Come down here, draw some sort of circle, draw another half circle, draw a line up the middle to show that they are not attached, draw a couple of blocks over here, connect these blocks to a battery. That way we get a current. So current will go this way. These would be probably referred to as carbon brushes. So the idea here is these are little blocks with a spring on them, and they attach to this rotating circle, which is cut in half. So this part is not electrically connected to the left part across this circle. And so we have current comes in here, goes up this way, goes up here, crosses over, comes back down, comes over here, comes through the carbon brush, and then back to the battery source. So we got two sets of current. So this first set of current is simply here to generate the magnetic field. So now let's look at how this current that's in this loop interacts with the magnetic field. So to do this, we use the same equation we've used for everything. I think it's the Coulomb's law and Lenzs law. Force electric equals QE plus QV cross B. So we're going to assume that there's no electric field, which is mostly true. But what we're concerned about is the QV cross B. So one of the definitions of charge, or of current, is that it's positive charges moving in the positive direction. We know it's really negative charges moving in a negative direction. That's okay. Crystal light. Okay. Or generic equivalent. So we have a positive charge here moving into the board. I know you're going to have to use a little bit of perspective. So we have positive charges moving into the board. So I'm going to do V and then something kind of like this. No, it's supposed to be an X. Bigger X. There we go. X. V is moving into the board. And the magnetic field is to the right. So what happens is you have V cross B. So you have a net force going down. Whoop, purple. So we have a force going down. And then we have V coming back on the other side. So V is the velocity, the speed of these charges coming back towards us. So we have, let's see if I can do this, V cross B. So you're going to have it pointing upwards. I know it's like an M.C. Escher painting. Drawing. And then along the sides, we're going to have no net force because the movement of the charged particles will be parallel to the magnetic field. Cross product is the sine of the angle between the two. And so when theta equals 0, when the two are parallel, the speed and the magnetic field, then the sine of 0 will be 0, therefore no net force. So what happens here is we're going to have a torque, a spinning, if you will. So we'll have a motion going around in a circle like this. And that's how you get like a generator, something that spins. Hook up the electricity, bzz, spins around. And this is there's a lot more engineering that goes into it, but this is the general principle that you'll find behind pretty much most, if not all, of DC motors. Motors create motion, generators generate electricity. And that's just a naming convention. You could also take this, and instead of having a battery, if you had some sort of motion, or like a crank or something like that, you could spin this loop manually, and that spinning that loop would then create an EMF or a voltage down at the charge. So this is completely reversible. You can either put in electricity and get motion, or you can put in motion and get electricity. Now, to look at some naming conventions real quick, you're going to have 4 terms that you'll see from time to time. You'll see, zoom out slightly, you'll see armature, field, rotor, and stator. So armature is where the current will go that produces the motion. Well, at least in this case. So probably better think of armature as it's what produces the power. It's the goal of what you're doing here. So in this case, when we have an electric motor like this, the armature would be in the middle because the current is going through the wire, the loop, and that's what creates the motion. So you can think of the armature as power producing. Now, on the opposite side of the armature, you'll have the field windings. These generate the magnetic field. So here we have the field windings on the sides. So we have field winding there, field winding over here. The entire purpose of the field winding is to produce an electric field for the armature windings. And so the armature winding then creates a magnetic field that then, or creates a either current or motion to interact with the field windings. Now, as a general idea, the field windings produce the magnetic field, the armature windings produce the power, whatever you're doing, either electrical or motion, depending on generator or motor. You also have the rotor and the stator. The rotor rotates and the stator is stationary. So the rotating loop in this case would be the rotor, and then the field windings would be the part of the stator. The field windings and the armature aren't always the same. So sometimes, depending on the design of the motor, they'll switch from one side to the other. The field windings, though, will generally have a smaller magnetic field than the armature. If you're trying to create something that's producing electricity or creating power, then the vast majority of the electricity will go through the armature windings. And the field windings will be there just to create an electromagnet, which will be relatively small. And as an idea in life, if you're having something that's rotating, it's hard to maintain that electrical connection, because here we're doing it through carbon brushes, and transmit massive amounts of electricity. So it's generally preferred through design if you have the smaller amount of electricity going through your rotor. So generally you'll try and see if field windings and your rotor together, but not necessarily, because you want to have when you have relative motion and trying to maintain electrical conductivity, it's more difficult. And so if you have massive amounts of electricity flowing, you want to do that through the stator, what's stationary, rather than what's moving. Though depending on design, not always feasible. And there's many different ways of designing this and engineering considerations. So this is just the general idea of, hey, here's a DC motor. So one of the key parts about when this rotates then is when this gets up to, let's say, halfway. So when you have the loop towards the top, this break in the, I guess the loop commutator, if you will cause the current to switch direction. So you see here that you have current going this way, over, and then back down. Well, when it gets halfway and then switches over, this break here in the way the loop is set up allows it to switch directions of the current. So what's going to happen then is, instead of having this downward current towards us over on the other side, it keeps the same direction of the current throughout the whole process. And what that allows to do is, that way the motor will always spin in the same direction the whole time. And this is due to what you call commutator rings, or brushes. And so these DC brushes allow the same direction of current the whole way. And that's one of the key parts of a DC motor. It's also one of the downfalls. One of the problems or challenges, having to commutate, switch the current every time the motor rotates, causes more wear and tear than if it didn't have to. And so that's one of the key elements of a DC motor and how it works. One of the you'll generally see DC motors will be a little bit bigger than AC motors, but DC motors are bigger. So generally you'll see AC motors are preferable if either one can be used equally. Now moving on to an AC motor, specifically a synchronous. You have, I guess, two broad categories, synchronous and asynchronous. And synchronous basically means that the AC motor will spin at the same rate as, I don't like that, as your alternating current. So if you have 60 hertz alternating current, then your motor, your AC synchronous motor, will spin at either 60 hertz or a multiple thereof, 120, 240, etc., etc. Let's do an actual circle. There we go. And this will be, no fill, but black. There we go. No opacity. There we go. So this is going to be my AC generator. Copy paste. Get another one. There we go. Line them up. Make one smaller than the other one. Reline it. Yeah, I'm good with that. So the idea here, there's many ways to do AC motors. The example I'm going to show is something like this. So it's going to be an AC synchronous where it operates the same way. And each of these circles, it's actually a solenoid creating a magnetic field. It's an inductor. And the magnetic field will change with time. So, nope, that one's too big. So for this, I'm going to have the coils are coming out towards us, and specifically in this case, the current will be coming out towards us. So be like, I'll draw a circle. This one's current's going to be coming out towards us, but less, so I'm going to draw a smaller circle. If you think of this as an arrow pointing towards you, this will be electric field going away from us. This will also be away from us, but less. And these will be 2 extra circles that I drew that I didn't mean to, and they will be done away with. Don't mean to be so harsh, but useless circles have no use to me. These are referred to as poles. You can actually have more than just 6. 6 tends to be useful though because we use 3-phase current often. And so the idea here then is we will have a, let's see here. So I will draw a electromagnet in the middle. Something like this. Oh, use copper color for copper. And now we're going to look at see what kind of magnetic field is generated by these poles. And I will use blue. So here we have the magnetic field coming out of the board. So if you do the right-hand rule, you'll have the magnetic field generated this way. So you look at a circle like this, and at the middle, the magnetic field will be going that way. I'm going to draw it over here though, just so I don't interfere with the drawing. So this is from this one. Now from this one, you're going to have a magnetic field going this way, but it'll be a little bit less. This one, to draw the circle, it's going to be coming down this way. Look at some of the others. Do red now. So now this one is going into the board. And it'll create a magnetic field going this direction. This one will create a magnetic field going that direction. This one will create a magnetic field going that direction. Move these over, overlap. And when you add up all these vectors, what you do is you get a magnetic field going strong in this direction. And since we have an alternating current here, these currents aren't stationary. Well, okay, they're physically stationary, but this is at its peak, and this one is going to be getting stronger. This one will be getting weaker. This will be getting weaker. This will be getting stronger, and it'll rotate around so that you can think of it then next time. This will be the strongest. That'll be a little bit weaker. That'll be small. This will be the strongest. And it rotates around. So basically what you have is, even though we calculated this magnetic field for one setup, it's going to in effect be rotating around. Like this. And if we have this electromagnet in the middle going this way, and this will be creating a magnetic field going this direction. Magnetic fields tend to align. If you have 2 bar magnets, they're going to align with each other. So what happens then is this center portion will feel a torque to align with this magnetic field that's generated by these external coils. And as the electrical current rotates around these coils, the internal rotor will then try to follow as well. And so this rotating magnetic field will then pull the rotor, the middle part that rotates, around in a circle. And that pulling it around with that torque is what gives you the motor action. And then we talk about field windings and armature windings. So you have stator on the outside, rotor on the inside. These are the field windings on the inside because the entire purpose of these magnetic field is just to create these magnetic field creates a magnet, which is then pulled around, and the armature windings would be on the outside. And that's the idea of a AC synchronous motor. Lots of different ways of engineering it and engineering details that go into it, the nuance, but that's the general idea. So the question then becomes, so if we have AC power and DC power, or AC electricity and DC electricity, which one is preferable? Well, they're really kind of used for different situations. The big difference is AC power comes from rotating machinery. Rotating machinery comes from a power source like steam, fuel, etc., 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 where DC power generally comes from, more or less, batteries. And the nice thing about batteries is they're a good backup storage of power. So almost everything will use, for the most part, AC power as their primary source, but then maybe some emergency equipment or some backup equipment will be DC, so that if there's a interruption of power, the steam trips offline or whatnot, the DC can then either help the system safely shut down, or it can carry it over long enough so that the AC power can hopefully start back up again and then take over the load. The main advantage of AC is you can have generally smaller generators and motors, and the power comes from rotating machinery. DC comes from batteries. Okay, so that's the kind of idea of where we get how we use Lenz's Law and a lot of the other stuff that you learned in actual practical situations. So that's the conclusion of the AP Physics exam for the electromagnetic portion. Wish you guys the best of luck. Appreciate you being with me and watching. I have plenty of other videos. Check them out. I appreciate it. Wish you the best of luck. Thanks.